You know, any category of this kind which has a terminal object collapses to a flat sum, or a flat set.
Right.
This you can do.
What's that?
Just sets.
Just set theory.
Just set with identities on each element.
Yeah, so it's true.
A set with just an identity on each element. No, zero structure.
Zero. Okay.
So you can't. This is a note result by Joel. The only Boolean categories are Boolean algebras, and if on top of that you ask, like this extra structure which is encoded here, you only get a set.
Yeah.
It's quite easy to prove that. You can't have terminal object here. No.
No, okay.
Oh, no way.
Yeah.
Your category just completely collapses. And because of the dagger you can't have initial, because this is just a categorical actualization. So let me just go to the passage from formula to picture. So we already had this nothing to 2. I go back, I see now adjoint. Adjoint for me would be picture upside down. So this is F from A to B. This is F adjoint, that's all. F adjoint. So here you see something with an adjoint, the thing going from nothing to something. Result, here it is upside down. And so the equality which you see in the commutative diagram here just means left side equal to right side. Now this looks like a very weird law until I do this. So what I'm just doing is, like, in my representation of my triangle, I sort of add this little piece of black line. I add it to the picture. It's completely innocent, because I decided how Mike was like that. I decided to represent my Bell state by a pink triangle. So now I add something to a pink triangle, black line. And now I don't pink triangle. I'm still being completely innocent, because you can imagine the pink triangle here and you can sort of think away this part of the black line. Now, what is sitting there is nothing more than, I'm going to use this one. What is sitting there, like, what you see there is this. Yeah? Yeah? Mm-hmm. Yeah? Yes?
Sorry?
Yank the rope.
Yeah.
Yanking a rope. Very innocent. Of course, here you feel that, like, these categories can be used to implement knot theory if you go with the braid, of course. Because that's exactly what you're talking about. So it's a very innocent law. It's really about yanking a rope. But this is like, let's just prove that you can define Bell states like that. So this is the formula we are after. So you've got an identity, you've got a Bell state. So let's do so. We've got a sum over pairs, yeah, and an identity on the left. Yeah? And now you see, you compose this with the adjoint. So the adjoint to this, I write it down, is the sum over j's of, wait, let's j here, and I'm going to put the other j there. Just calculatively that this thing corresponds and this thing corresponds. Oh, sorry, I'm wrong. We should, here, these are adjoints, so I have to reverse the sign. So here you see, I get a delta ij. Here, yeah, delta ij. No,
I'm lost a little bit.
Well, usually you would write this like this. But I rather write this two-dimensionally because that's the structural essence. But maybe I should write like linearly, like you would do it in the Messi-Dirac stuff. Yeah? And this is, so I'm just going to take a form of composition here. So here you've got identity, Bell state. Yes, we agree? This is Bell state. Huh? Yeah. Identity, Bell state, and this is adjoint Bell state identity. That's adjoint Bell state identity. Yeah. So and here, now if you calculate this, then you see that here you've got an I, cat, j, bra. This just gives you a delta ij. So the overall thing is an identity from here to there. So it's true in the open space. Due to this silly calculation. Now, the big surprise is how much structure this little easy to verify thing calculates within it. So it's really so I use a property of Bell state, which is this one, and I take it as a basic definition of my quantum mechanical formula. And like it's incredible how much linearity, aspects of linearity are encoded within this. While there's no vector space structure or anything of this kind here, there's an amazing amount of linearity sitting in here. And like and exactly what the fact that if you have a thing like that and you've got a terminal or initial object, thing collapses completely. If you've got a thing like that, you've got a diagonal, thing collapses completely. Linearity means like, what is linearity? Linearity means like lines beside each other, not stuff like this. This is non-linear. This is the diagonal. From one thing you go to two things. If you have something like that in such a category, thing collapses completely. So it is it's an implementation of linearity. It forces you to be linear in some other way than writing down the whole vector space business. So that's where we are now. Now we're going to start, because people are talking about star, tensor, blah category. So this was a definition. So this was the definition of the category. Now this is the definition of an operation. I define a new box called box star by taking this picture. I can just take, so now I can use my pictures to define things, because it should be clear that my definition is purely a graphical definition if I want to. Like this thing was just putting pictures upside down, and this is just the triangles. And the other part of the definition, symmetric monodal category, was picture calculus. So at the moment I can do everything purely in my graphical language. So I define something here. So for every morphism A to B, I define F star from B star to A star. Yes, and it turns out that this gives you star autonomous category structure, for those who know it. Star autonomous category is due to bars. Now, so you can do something else. Instead of putting F here, I put F adjoint. Yeah? Why do I do this? Because now I'm starting to calculate. So I defined this thing, which I said gives you star autonomous category. This is something else. This is actually the thing which Kelly didn't have, this little part. But now I'm going to compose these two things. So how do you compose these two things? Like, I compose these two things by putting here now this lower star and then putting this picture within it. That's what I'm doing here. So I'm doing the composite of these two star things, which means like nesting these two pictures within each other. This is what I get. And here you see this thing which I can yank. Here again you see this thing which I can yank, and what you see that the composite of these two operations gives you exactly the adjoint. So these two operations which I just defined end up being factors of the adjoint. Yes? Okay, so we have this, and in Hilbert space terms they exactly correspond to transposition and complex conjugation. So in my abstract setting I've got a witness both for transposition and for complex conjugation. So these are things which you know from linear algebra. So I don't need all this linear algebra to have these things sitting in here.
Yeah.
There is no numbers, but I mean a witness of having the ability of having complex conjugates. So you can encode things here abstractly where you typically would use complex conjugation for.
I mean, for Hilbert space, both transposition and complex conjugation, you need to consider both as a complex, both have a complex in a product and a linear product. Which is, I mean, why do you want to decompose your adjoint as something where normally in Hilbert space it would just be in one go?
I don't understand the question completely.
No, I was just thinking.